Hey folks, in this video we're talking about empirical formulas and molecular formulas. Yay, lots of formulas. So sweet. We got a few objectives here. I would like you to be able to distinguish between empirical formulas and molecular formulas. Already covered, but hopefully we can talk about it a little bit more. I want you to be able to determine molecular formulas if you're provided with an empirical formula and a corresponding molar masses of a compound. And I want you to be able to use mass percent composition or percent composition by mass, same thing, and molar mass to determine the molecular formula for a compound. Cool. Let's talk about how to do that. Molecular formulas and empirical formulas. Just a quick refresher. A molecular formula describes the full formula for a compound. That's going to account for every atom inside that compound. Here's a lovely compound. This is my friend cyclohexane. And the molecular formula for cyclohexane is going to count every single atom in this sucker. So we got 6 carbons total and 12 hydrogens total, giving us a molecular formula of C6H12. Nice. Well, the empirical formula is a simplified formula, and this is going to be obtained typically from a percent composition, which we'll talk about how we actually get that in a little bit. But it's going to use the ratio of the elements in the smallest number possible. So here, our ratio we would say is 6 to 12, but that could be simplified. We could make that a little bit smaller. So for the same cyclohexane, my empirical formula would be C1H12 or just C. Did I say 12? 2. C1H2 or just CH2. And that's like I divided both these numbers by 6. I simplified that ratio because, if you want to simplify a ratio, you have to change both the numbers in the same way. Anywho, let's talk a little bit about how we can get the molecular formula for a compound if we know its empirical formula and its molar mass. These are conditions that we might have set up, and we'll talk a little bit more, again, about how a scientist might find themselves in this situation. But if you find yourself looking for that molecular formula with both of these two bad boys, what you're first going to do is get the mass of that empirical formula. So for this example, let's say we have an empirical formula of C2H5NO, and we know our total molar mass. Well, I'm going to start by getting the mass of that empirical formula. So look at the molar mass of each of the elements, and then multiply that by how much of that element is there. So I have 2 carbons, I got 5 hydrogens, oh my gosh, here's the molar mass of nitrogen, I only got 1 of those, and I only have 1 of these oxygens. Well, I can add all these numbers up, and bam, I have the mass of my empirical formula. Wow, just like we can see with that CH2, in fact, let's go back to that for 1 hot second. Here, this CH2 describes kind of 1 unit. Here's a CH2, and I can see there are 6 of those. So I know that my empirical or molecular formula is 6 times my empirical formula. My molecular formula is 6 times my empirical formula in this case. Well, we want to figure out how many times larger our molecular formula is than our empirical formula here. And so the way we're going to do that is we're going to divide the molar mass that we have, this guy, by the mass of our empirical formula that we just calculated. That's going to tell us how many times larger the molecular formula is than our empirical formula. So we'll just do that, and we should always pretty much come up with a whole number for this calculation. So here I have 4. This tells me that there are 4 of these empirical formulas inside that total molecular formula. So multiply all these subscripts by the number 4. Shazam, take my empirical formula, multiply everything by 4, and now I have the molecular formula. This tells me that there are 4 of these units in the overall molecular formula. Let's do another problem. So we're going to do the same gosh darn thing, and here's our example formula. Wow, that's a much larger formula, and wow, that's a huge molar mass. But let's figure this out. We're just going to follow the same process. So we'll get the mass of this bad boy, the empirical formula, first. And again, we'll just look up the molar mass of each element and multiply that by how many of that element are present in the molecule. We got 2 fluorines, we got 5 chlorines. Okay, neat. That's a lot of mass of chlorines. Let's add all these chlorines up. That's a large percentage of the composition right there, I tell you what. We have our molar mass, or now that we don't. We have our molar mass, but we have the mass of the empirical formula. Well, now let's divide the molar mass by that number, and that'll tell us how many of these bad boys are in our molecular formula. How many of these empirical formula units add up? Cool, so we divide, we get a nice whole number of 9, very nice. And so now we can multiply the subscripts in our empirical formula to get the molecular formula. Okay, so I'll multiply, that little 9's trailing off, and now it's covered up. But when I multiply that out, I get this molecular formula, and wow, that is a huge molecular formula, 45 carbons, 45 chlorines. It's a lot of carbons, a lot of chlorines. All right, well, let's look at some weaponized cats. Back in the day, people thought that you could maybe make some weapons out of cats. They were trying to strap rockets to them, and today, scientists are still working on solving that problem. Anywho, if we want to use the percent composition of a compound and use that to get the molecular formula, this is something that a scientist human might do in real life. If you had an unknown compound, you could analyze that thing and you could figure out the percent composition. And you could also use that to figure out the empirical formula for your, the molar mass for your compound. So you can figure out percent composition and molar mass. And then with those two things, you can figure out the molecular formula. The first thing you're going to want to do is follow our usual percent composition grind. We're going to convert our percentages to mass, mass to moles, divide by small, multiply to a whole. So let's turn those bad boys into masses. We also are going to need to know our molar mass, but that's going to come into play next, after we have our empirical formula, because we already know how to use empirical formula and molar mass to get molecular formula. So yeah, we converted percent to mass. Let's convert those masses to moles using some sweet X lines and some molar mass action. Bam. Well, now we know we have to divide by small to get our smallest ratio. Okay. So 2.94 is small, so we'll divide all these bad boys by 2.94. I'm going to round that to 2, yeah, because if we're within 1/10 of a whole number, we should just probably round up. Okay, and now we're going to have to multiply to a whole, because this is not a whole number right now. So 0.33, that's a third. I'll multiply all this stuff by 3, and that, well, yeah, if I try to, yeah, it doesn't work out so well. So I guess I'll multiply all these bad boys by 3, and that should give me my nice empirical formula. Sweet. All right, well, now I have a molar mass. I have an empirical formula. I know I can use these two things to get my molecular formula. And we'll follow the same process we did before. So I'm going to use that empirical formula that I had. I'll get the mass of that bad boy. And from that other slide, I'll just drag back my molar mass, because I'm going to need that. So I'll divide the molar mass by the mass of the empirical formula. That gives me 6 as the ratio between my empirical formula and the molecular formula. Oh my gosh, I'm going to multiply all my subscripts by 6. Shashow. I should have my empirical formula. Wait, I screwed up there. I did 3 plus 6 for the oxygen. That was dumb. Anyway, that's the end of this video. I hope you understand how you might use the percent composition and molar mass of a compound, something you could acquire using a technique called mass spec. Maybe I'll make a video on that. Anyway, yeah, ta-ta. Have a great rest of your life. Oh, it's the end of the video time, right? It's really not a good piece of software. I don't recommend it.